All right, so now we will create an ETABS model that is similar to the RAM structural system model that was created. And when we start ETABS, this is the user interface that we are presented with. It's very straightforward. So to start a new model in ETABS, click on New Model, self-explanatory. We get the model initialization dialog box. In here, you have three options, and they're basically related to the settings that you use. So here's where you can kind of customize your settings based on the project that you're working on. We're all good with these settings. We will be using US customary units, AISC 14. We can also switch up to another version if that was desired, or other codes, foreign codes if we were in a foreign country. Still design code will be AISC 36010. Again, you can choose whichever you want it. And the concrete design code is AISC 31814. Information is provided here on the side. Gives you a brief description of what these settings are about. All right, say OK to that. And we have the option here to essentially use a template to help us model our structure. And what I typically do, if possible, if the structure is very uniform, I use the template. In our case, that is the case. You don't have to use the template. You can cancel out of this and then define your grid manually, but I use the template for our grids. So here, the uniform grid spacing will be the number of grids in the X direction will be 4, in the Y direction is also 4. In the X direction, if you recall, our structure here is each grid spacing is 30 feet. It's a 4 bay. 30, is it 4 bay? Yeah, it's a 3 bay. Apologies. 3 bay, 30-foot space bay structure in the X direction. And in the Y direction, we have 25-foot bays, just so that we can add some variation to the analysis. The grid level labels in the X direction, we are starting with A, so we're good, and it labels it from left to right. You have obviously options to do it the other way. Same thing in the Y direction. You can go from bottom to top or from top to bottom, and we will start with numbers from bottom to top. This will be consistent with what we did in our other model for RAM structural system. Say OK. The story data will have one story right here, and the height of that story will be 15 feet. Bottom story, we'll just put 15 feet just in case this thing does something bonkers. But typical story, if you had more than one story, or what would be the bottom story, oftentimes the bottom story is different than your typical story. And so this dialog box allows you to quickly generate these story heights with the variation in spacing. And so here it's asking me, what am I adding here? You know, I'm adding really just this grid because I want to do everything from the beginning and show you how to create columns, beams, and slabs and things of that nature manually. But some of this stuff can also be automated through these other options that are available. All right. So, okay. Once that happens, we are given three windows. There is a Model Explorer window, which acts very much like the window explorer that we're used to in terms of file tabs, and you can search through this, that, and the other. Um, and it's the exact same thing as far as the functionality. You have these different tabs, which are kind of self-explanatory. We'll learn more about it as we develop our model. We can adjust the width of this window. We're given a plan view to operate in, or a 3D view to operate in. So just for a second, I am going to operate in a 3D view, and then I'll change to the views that I need to be in order to create the elements that I'm working on at the particular time. So I'll close one window. You always have to have one window open in ETABS, or else, as far as I can recall, the program will close off or something like that. So you need to ensure that you always have some graphic view open, or else what are you doing, right? So here you can see from the graphics that we have a white background and blue grid, if you will. This blue grid line is really what they call the horizon, and it lets you know the where is the 0, 0 plane for y and x. Where's the xy plane 0, 0? As far as I can recall, that's where the horizon is located at the base of our structure. In this instance, as you would expect, this is mimicking the ground, so to speak. So this can actually be modified. I don't like the white background oftentimes. I'm used to a different background setting. So from our options menu, we can go into graphics color and look at our display options. And we're set with this dialog box here. We can change the color type of these elements. We can also modify transparency. That's the level of see-through and darkness for these elements. So I like I said, a black background. Once that option is selected, obviously the color should change so that it could correlate to a black background. And again, these can be adjusted on a user basis. Say okay. And I will also turn off my horizon by really I can go to from the display menu. I think you well you can use this dialog box, set display options. You can use that toolbox rather. So right here under special items, under the general tab, turn off the horizons. There's also the object assignments and other assignments, and this is all related to the views. So it's all related to the graphics on the screen. You can apply it to all window. Somehow when I do this with this software, regardless, the horizon gets reset, and it's a constant back and forth with the horizon and the user here. So, but we're okay. The joint objects, we can make them visible or invisible. Here I will make them visible. Say okay. And this is our starting point. We see we have grids A, B, C, and D, and 1, 2, 3, and 4. So let's enter a plan view by selecting plan from our icon here. For story, say okay. There we have it. All right. So the first thing I want to do is define materials that I will be using here. When I say materials, I mean material properties like concrete and steel, and the different grades of steel. You do that from your define menu. These are all our preset materials that came with our defaults, if you will. So we already have 50 KSI in here. We have a concrete material in here, 4,000. We have reinforcing steel grades at 60 KSI. and we have post-tension cable steel grades at 270 KSI. So this will be good for what we're going to do, but just for addition, adding material, an example, we're going to add another 36 KSI material. And we do that from the procedure that you just saw. And we say, okay, here, the box is self-explanatory, but basically it gives you general data information, uh, material weight properties, mechanical properties of the material, and any other design property that's related to the material. All right, and these are some of the advanced material property data information. You click on them. When the time comes for you to use it, you will know. But it's not necessary for our example. So, okay. All right. Again, now let's save the file. This thing is processing. It's odd. Guaranteed something's related to the networking here. All right. So anyway, we're in. Save it on our documents, and I am going to call this folder ETABS. Assess. No, ETABS. Actually, I already have an ETABS folder, so forget about that. Let's just go in here and see what I have. Okay, create a new one. Give this a file name of 0709 2019. Let's see. It's going to give a file name similar to that what we had in RAM, which I do believe was something about a simplified version. Hey, let's not waste too much time here. So we're gonna say, actually, let's go ahead and waste time. I always go back and forth with myself about this. Let's waste a little time and get the name right. I want to do the same thing we did in RAM. Okay, personal tutorial model, standard building phase 1. All right, kill it. Personal. Okay. All right, so let's start defining some elements. All right, so columns are defined. You actually need to input section properties, now load them up in the software. Again, these are all preset, so if it wasn't preset, I would actually import them using the import new properties value, and I'm going to select AIC, and I'll just go ahead and import all of my W sections here, just so I can ensure that I have everything I need when I need it. So, okay. When you do this, your materials default, you have to be aware of what's going on here, because this will be applied to all of the section properties that are being inputted. So if this was, for example, concrete material by mistake, you would need to you would need to adjust it later, because it would have those properties. So, or A36. So be aware that this is a critical dialog box, and you have to ensure that you're selecting the right material. Say okay. All right, let's put in some columns. So once I click this icon, quick draw columns, I'm able to lay out some columns. I could also do that from the draw menu by going to draw and draw beams and columns objects, and here quick draw. These icons are available right here for easy access. Now the property that I'm going to use here should be selected as a my W shape. If it's just a lateral column, that's actually a generic name that's used for lateral columns, and it might have some preset lateral columns that are available within, like a group, available for selection by the computer. But we will use 14 by 90s, just like we did in RAM. 14 by 90s. All right, so now we're good to go, and we can start drawing our column. We could do it one by one, or we can click and drag a window around the grids, and then insert columns at those locations. Save the file. All right, the other thing, let's just ensure that we have some of our generic settings that are required, if you will, later on down the line when we're doing design. But just to say, when we get into these softwares, oftentimes the best thing to do is to make sure all your settings, your defaults or codes, design criteria is correct. So for our steel frame design, we'll go into our design menu and select View/Revise Preferences. These are the default preferences that came with the model. You scroll through and you can read about each one of these 38 items, but they're self-explanatory. Building code is selected, or steel code in this case. The frame type that we're going to use, that's a SMF stands for special moment frame. We're going to use an ordinary moment frame. Seismic design category is set here. We're going to use B. Importance factor, we'll keep it as 1. Row is 1. SDS will be 0.143. You know that from experience and from our code analysis. 3 will be our R value. Omega naught will be 3. Our deflection application factor, CD, will be 3, because this is a lateral, a steel system that's not specifically designed for seismic resistance. Our design criteria will be ASD, all-time favorite in North America. We will be using the direct analysis method. Here we can change to various stability design methods. Direct analysis is what we'll be using. We could discuss this later in general, but the intent is to use the direct analysis. The second order analysis method, we're going to use a general second order analysis method, which is an elastic second order second order analysis that's created. We could use amplified first order, so-called B1, B2 method, but we will be using our general second order elastic analysis when the time comes. This is just a general setting so the computer can know what to do, but this has to be coordinated with other parameters in the software. So tau sub b, uh, we can fix it. We can have it variable, or we can not have any modification at all. Okay, so I'm going to use a fixed tau sub b for now. You can, actually, let's use a variable, and then we'll see what the computer does, and then we'll go back and fix it later. All right, do we want to add notional load cases into seismic combos? No, we don't, because of the structure. We know from experience doesn't need that. The beta factor is related to buckling restrained braces. Beta omega factor, also same thing, buckling related. Regarding buckling restrained braces, we don't have those type of elements in our structure. Omega, these are our factors of safety: bending, compression, tension, shear, etc., etc. So it's really self-explanatory. It will be right. It's a good idea to get into this in detail and read it as an engineer, so you can understand what's going on. Question is, are we going to ignore the seismic code? Yes, because we're in seismic design category B, and our structure is not specially detailed or anything like that. We'll be ignoring that special seismic load as well. Are the doubler plates plug welded? Uh, we could leave these as defaults. It's not going to affect the analysis. Other things here, like I said, you have to read into it in greater detail. We're going to consider deflection here. We're not going to consider deflection, even though we are considering it deflection. But this is just letting you know that you can limit your beam sizes or include service ability in your analysis here. Because we know these member sizes will work, I will not be considering deflection at this point. We'll go back and turn this on later. But actually, I'll leave it. Let's just go ahead and leave it. So for the critics, might think that we're just looking at strength analysis only, we'll leave it. But this can create some issues sometimes, and you have to get into it and to verify. But you really shouldn't be considering deflection and running analysis, a direct analysis at the same time, because you're using reduced moment of inertias. All right, just for critics, we'll keep it for now. And our capacity, we'll bring that up as far as demand capacity ratio. We'll bring that up to 1. Some people like to use a lower value to allow for some increase in the future. We're not going to do that at this point. Say okay, but typically I would, for actual design, I would lower this number to probably even 0.9 sometimes, but 0.95 is a good number. There are many factors of safety that's already included in the design, so technically you can go up to 1 without a problem. But sometimes you have to leave yourself room for error. Maximum number of iterations, here's a description of that item, and it's nothing that will affect our analysis. So okay, save work. All right, some other things, just as far as when we get ready to analyze some of the generic settings that are set here. Um, when obviously we run a check on the model, but we could get into degrees of freedom, which basically tells us if we're doing a full 3D analysis, a 2D analysis in the X and Z plane or YZ plane, or if we consider no rotation at all. All right, so we'll do a full 3D. So that's what we're about. Save. All right, that's the bulk of what needs to be set here, let's continue drawing our elements. So now we'll add beams using our quick draw, or like I said, we can go to this menu, quick draw, add these beams. They'll be frame beams. I'm gonna add them as pin. We could set the releases right here in this dialog box. We'll add all these beams in right now as 21 by 44s, and then we'll adjust the property afterwards. All right, 21 by 44. And once you hover over the grid line, you can see it pop up. That blue line indicates a green will be framed in between those support elements. I don't know if you click and drag. No, you can click and drag. So let's just do that. Let's make sure this thing didn't double up here. Delete that. Gives us the opportunity to copy a beam. So I'll take this beam right here and I'll copy it over. I will copy it using the replicate command, and I'll copy it over 30 feet in the X direction. One time, apply. Now I don't see the beam sizes, but I can easily turn that on. Going to that options menu and labels or sections for our frame assignments. They apply, turns that on. Could also really take a look at the in releases to see what has been pinned or what has some type of release property set to it. Those green dots represent some type of release. Right. So there we have it. This is the main frame. Let's go ahead and make some quick adjustments. We know that the beams frame in north-south on our page are actually going to be, well, we're actually set to be 18 by 35s. So we'll be consistent with what we did in RAM. Again, this is just an example. I know ultimately I will have a deeper beam framing into a shallow beam for this example, but it's just an example. In the real world, I mean, even though that can occur, I would make the beam depths at least the same depth if necessary. Most of the times I will always do that. All right, in an unusual situation, I'll accept a deep beam framing into a shallow beam and adjust the connection accordingly. But anyway, to change these properties, you have to select them all first, and then you go to the assign menu, go to frame assign section properties. You can just type in the property you're looking for, 18 by 35, and it pops up. Double click on it, it's assigned. Save the file. Let's go ahead and change the stiffness or the boundary condition, if you will, for these beams. We'll change their connectivity to the columns. Right now they're pinned. If I click on one of these beams by hovering over it with my pointer and right clicking, I get this dialog box, and you can see the in release settings. Torsionist release, moment in the 2 direction and 3 direction, which is basically weak axis, strong axis, have been released. And there's a number of other information that's provided with this beam through this dialog box. Geometry, any loads that were on the beam, that would be on the beam, design, etc. Say okay. So with the beam selected, I will go ahead and change the properties to no releases using the procedure you just saw. Say okay. Now they're fixed. Save it. Let's go ahead and put in some infill beams real quick. Again, we'll use our 21 by 44s in the long way and 5-foot spacing. There we go. So it's 5-foot spacing. So the number of beams, 4, I believe. And this orientation, is it parallel to the Y or parallel to the X or T? You have to read about what they mean by T and R, but basically you could have it parallel to the X or Y direction, and you can modify it depending on your framing. When you put your cursor over a base size, it generates these red dotted lines, dashed lines that indicates your framing. Also, the moment release will be pinned. So with that, you can easily create all of these infills. Right click, you're done. Save your file. Let's take a look at this thing in 3D. And when we do that, you see the horizon pop back in. I'm going to turn it off for a second, just because I want to clear up the drawings a little bit more. You can see that the column supports at the bottom of the column. They have this symbol that looks like a triangle, which is basically pinned in that direction. I believe you can select the joint, right click on it, and it tells you the restraint. So it's pinned in the X, Y, and Z. Cancel. We want it to be fixed because this is where our portal frame is, our moment frame. So we'll fix these supports by selecting them first. When they're selected, they're kind of highlighted. It's hard to see, but you know they're selected by this message area, if you will, in the bottom left-hand side of the screen tells you what has been selected, or if something's going on, the computer's trying to correspond, which is software's trying to correspond with you. Some of the messages appear right here on the bottom left side. Anyway, I have 6 joints selected so far. I need 8. I'll be rotating this and selecting the other 2. So that's all 8. You rotate by your settings, but basically shift and middle mouse. It's based on your mouse settings, but shift and middle mouse should be the default for most items. Middle button, rather. All right. So with that selected, I can assign it's a joint, so you have to assign joint properties to it. Restraints. So apply. Now these are all properties related to joints. You know, when you get to the assign menus, everything that you can assign to joint is there. Everything that can be assigned to a frame object is there. Shell, link, right? Except for loads. Now loads, again, separate areas for it, for joints, frames, and shells. Right. Save your file. Okay. Let's do a quick model check just to see if we have any issues that the computer would like to tell us about. We'll do that by going to the Analyze menu and do a model check. You check joints, frame checks, shell checks, other checks, and exit to fix things. So I'll select everything, even joint story assignments, even things that don't apply, and say OK, see if anything pops up. So the model has been checked and I don't have any warning messages that were generated. So far so good as far as this stage is concerned. Now, different from RAM structural systems, we're not going in and out of models. They don't have a gravity module for beams and columns or frame or anything like that. Everything is done within this one area of the software, so to speak, with all the menu selections that are available. All right, so that's just a FYI. One thing that we need to set is our mass source, and that's for generating loads, seismic loads in particular. So where are the mass? What are we getting our loads from? Are we getting it from the elements that are modeled, or are we getting it from loads as well as the elements that are modeled? So if you don't have any, for whatever reason, any defined loads in your structure, uh, you would just use the self-weighted structure. All right, now by default, the program gives us this one mass source property that has been set. You can modify it, or you can create your own. All right, so I will modify this, and I will just call it mass source dead load, or loads, I should say. Okay. So I will get I want all of my dead loads, my masses from the dead load. All right. If I had different load patterns, I could add it. But here I'm just only going to do dead load for mass. So say OK. In fact, I'll modify this name just so that I'm clear. That's important for load derivations, self-weight derivation in particular. All right. Now, okay, so that completes our beam and column frame elements. Let's go ahead and model in a deck, if you will. So I will go to our first story plan view. And again, we have to define the section property before we can create it, model it. So what type of property we want here is going to be a deck section. And again, software always has something by default. You can modify that or create your own. So I'll modify that, name included. I'll just call it unfilled deck. Okay. Select unfilled for the type. I will select 36 KSI for the deck material. You see it's a membrane type by default, which is very important. All right, so you can read about the type that will be selected, but it's a membrane here, so I have membrane behavior. All right, which basically means it has in-plane deflection properties or in-plane stress properties. All right, but read about it to learn more. So here we will use, just as far as the height of rib, these are property data that can be taken from manufacturers. We can leave these placeholders, or just put this as 6 inches. Actually, we already have some. Going to the manufacturer, we can figure out what this information is for roof deck, but let's just throw some numbers out there. Placeholders. The design shear thickness, I'll put it as 0.358. This is the same as the equivalent thickness that we used in RAM. And for the deck weight, use 3 PSF. Now notice that we're not asked to use a Young's modulus. Well, that's because it's grabbing Young's modulus from our deck material type here, 36. All right. So the engineer really needs to go into the discussions of these software manufacturers to figure out, you know, the proper material settings that are required and why RAM would do it one way and ETABS will do it another, and do the results match up or does it make a difference one way or the other? You should be aware of it, but in my experience, this is not making a significant difference in the global frame analysis and the results that I've received. So it's worked so far, and it's worked by experience, not just in theory. Uh, so I've done a lot of buildings with RAM as well as with ETABS, and everything is still standing. Thank God. So okay. All right, so we say okay to that. And then now we will go ahead and place the deck in the model, save the file. All right, here we go. We can again go to the draw menu, draw a floor or wall object, and you can either use a quick draw, which is interesting, or you can do it point by point if it has some type of weird um, perimeter to it, or weird shape, or rectangular shape, however you like. I like to use point by point because for me it's always been reliable. So just move the mouse over and go to the point. You can see information that pops up like that next to the cursor. It says, you know, what point you're at. It's just kind of hard to see at the scale, but you're at grid point A1. Say OK. And then for the last point to close it up, you can either click C on your button, or the final point, where you began at. I like to click C because that typically does the job pretty well. Let's see. It's not doing it, so click the final point and it does it. All right. Now, what are the properties of this slab? So I wasn't paying attention. When I created it, this dialog box popped up, and I actually put in this property. So this is a great opportunity to modify an existing shell element. So I'll close it. So I don't want to use slab 1 because slab 1 is actually a concrete slab here. So I can modify it by going to the assign menu, shell, deck section, and picking unfill, say apply. Okay, now I get this symbol right here that lets me know I'm using the unfilled deck. Just to clear up things a little bit more, let's turn off our section names. Unfilled deck is there and it's showing me that it's spanning left to right. I really wanted to span up and down, so again I can modify that by going to assign shell and then changing my local axis. I can rotate it using this dialog box from its current orientation, 90 degrees. Click apply and it changes. Save. Okay. Now one thing I want to do is apply a generic mesh to my frame elements. Make sure all my frame elements are meshed. Now that I have the structure defined, I kind of want to ensure that it's all connected using finite elements. So I can select them all and then go to the assign menu, and for frames I can come down here and say frame AutoMesh Options. I like to mesh it at the intermediate joints and at intersecting frames and edges, and say OK. So I did it for frame elements, the beam elements, and column elements. Now I want to do it for the deck element. That's the shell element. So again, I select that, go to assign, and come down here to floor auto mesh options. The mesh option that needs to be selected, or I like to use, is auto cookie cut. the object into structural elements, and I actually will show you guys something interesting that I would, select all these, and then you can subdivide the element into other smaller elements, right? So I'm just basically saying, don't give me a element size greater than 4 feet here. There's something interesting that happens with ETABS that this setting is related. That's related to this setting, and I'll show it to you in a little bit. But basically, if this value right here was really small, and you had the membrane type that we have with such a small thickness to it, we get enormous deflections. And so there's a way to moderate that using the size that we have, the mesh size. So anyway, I'll set it at 48 inches for now, which is 4 feet. Say okay. That applies it. Save it. Let's go ahead and do a quick check. Everything appears to be fine. Now, for our loads, just to show you what we have here, we also have P delta options. We're not going to get into that just yet, but we will in a minute. So um, what we want to do is, in modal, of course, we'll take a look at our load patterns here. By load patterns, that's ETAB's way of inputting individual load cases. Patterns is the name that they use for whatever reason. All right, so this is already defined, dead load pattern, live load pattern. If I wanted to bring in a new one, I would give a name here, like, for example, superimpose dead load. And then I can change this to super dead, and I can add that load, right? But I'm not going to do that right now. Just keep it as it is. So right now, the only loads patterns that are defined are dead and live. And actually, the only load that I have in my structure is self-weight. So at this point in time, I like to run the analysis just to ensure that I can complete the analysis and I'm getting, I guess, some type of generic behavior out of the structure that I expect. And so if you have any issues with your model, you'll find out at this point. The other thing, like I was saying earlier about the meshing, is in settings, there's the mesh that we have. Now notice that the floor mesh was set over there at 4 feet. Over here it just so happened to be 4 feet as default just as well. And it's essentially two places where we're defining our meshing options, which is interesting. But here it's just basically saying to use a rectangular mesh and of course localized meshing where possible and merge joints where possible. Approximate mesh size would be 4 feet max. Say okay. Important note, these settings apply to all slab type shell objects in the model that use auto meshing. Right. So this for auto meshing, I guess, and what we said was for cookie, auto cookie cut. So okay. Run the analysis by clicking on that arrow button. All right. So right now everything looks to be behaving correctly as expected. This is once the analysis is ran, we have a deformed structure presented to us. The dead load case is what's shown here in parentheses. We can animate it just to ensure that, hey, it's kind of doing what we expect it to do, and it does. Deform it kind of uniformly greater in the perimeter than the interior as would be expected because we have these moment connections here. More this way, north-south, if you will, than east-west, because that's where all our girders are. Loaded that. Stop the animation. Save it. So far, so good, right? Okay, so let's, in order to make modifications to the model, you have to unlock it. After after analysis is ran, and it tells you that basically doing that will delete your results. We're fine with that. We're starting to just we need to make modifications. All right. So as promised, let's take a look at what's going on with our shell elements. Here now, the deck can extend beyond the perimeter. We usually have some type of extension, 8 inches, 6 inches, 1 foot, something. But the deck, it goes beyond the center line of the beam. We can model that in ETABS as well. So we save it. And I'm sorry, so we select it and then we can go to edit and edit shell and expand. And it's asking us basically how much you want to offset it. It can go inside or outside. So it could shrink it or you can increase it. Here our offset value will be 12 inches, just like it was in RAM. We'll apply that and you see our deck grows. Save it. Now without making any other modifications, I'll run the analysis so you can see the behavior. Okay, so analysis is complete and then we'll start our animation. And there you have it. Okay. Well, so far so good. So stop. Now, let's say we were to do something fancy like trying to decrease our mesh spacing here with our properties. We'll do that by selecting it and let's say we decrease it to something like a foot. We want a tighter mesh. We want to try to get really detailed in our analysis for whatever reason for our decking. So set OK to that. Let's go to our assign, our analyze, and check what happened here. Nothing happened. This is still at 4 feet. Again, I guess this applies to our AutoMesh setting. We at auto cookie. So if we go to assign again, shell, floor, we're at auto cookie cut object. So cancel. All right, run it. Let's see what happens. Well, you can see right away it's taking a lot longer because we created more elements. And we'll just investigate the behavior of what we've done. Oh, by the way, it creates modal cases by default just as well. So it's doing a modal analysis just as well. All right, analysis is done. Saving information. A lot of this stuff is going on right here. Figure out what's going on. This is the displacement. Now notice your displacement. Okay, here's the minimum displacement. It's a whopping, I can't even read that number, but it looks like to be on, let's say, about 4,573,367,286 inches. Bananas. You start the animation. So you know when that happens, something's wrong. All right. So the moral of the story is you need to keep this mesh size reasonable. 4 feet works for this type of. It's not always the case, but this is the case for this type of thin, very very thin shell that we've modeled. So go back and change the mesh options here. Put it at 48 inches. Apply it. Say okay. We're good with that. That works perfect actually. Save it. Okay. So now let's go ahead and put some load on the structure. by some additional load, but we'll put it by and placing it on that surface load on the deck, just like in RAM. We'll select the deck here, then assign these shell loads to it. Assign uniform loads on the shell load, gravity, dead load, 25 PSF. Here, be careful about this option. If you have existing loads here and you were to keep it on replace, it's gonna override it. If you use add, it's gonna add it to the existing loads. If you delete it, that's a way to delete all your loads. So replace, which is basically overriding anything that's existing. So say apply, we're good there. Select it again and put some live load on there. Change the load pattern name, change the value that you need, replace. Again, the direction is gravity, but it can be any one of these options. Gravity obviously means vertically down. You can say OK. Save our work. And let's go ahead and run some more first order linear elastic analysis. So I kept clicking this button right here to run my analysis. I could do it using F5 as it says as a shortcut, or I could go to the Analyze menu and then say from here, Analyze, Run Analysis. But what am I running do I know, right? So in order to figure out what you're actually running, here's the load cases that will pop up, and it's this dialog box that tells you what's going on. So here's the case that's being ran. It's a linear static analysis, first order. For dead, for live, we have modal in here, and it still has superimposed dead load. That's a linear static analysis, even though I created it, then deleted it from my load pattern. What happened is, even though I created it and deleted it from my load pattern, load cases are actually what gets analyzed, which are basically load cases are a function of load patterns. So these load cases are created using the define menu and go to load cases. From here, again, these are all by default. Whatever the load patterns that are created by default, you're going to have a linear static analysis for it. And you can modify that. Take a look at this. You can see if I click on this and let's modify show, it's probably empty. Right? So it doesn't really mean anything, which is odd. It's weird that it would even have it there, but delete it. For live load, if I modify it to see what's going on here, the load type is a load pattern, live load, scale factor 1. So this is my live load. There are other values here, P delta settings. We don't have any. It's the first order linear static. Same thing with the dead load. It will look like the live load, but the only thing is the dead load. All right. Say OK. Check out the mass source. Say OK. And mass source dead load. OK. Save it. Let's go ahead and run it. All right. So one thing we want to do a quick check just to ensure that we're coming up with the same results as ETABS. We'll check the self-weight of the structure. Interestingly enough, this is taking longer than expected. One of these settings might have went back to something weird. That's the thing with this software. It's always a back and forth issue with it. Sometimes you change one thing and for whatever reason, the computer thinks you changed it all. Okay, so here it's thinking that my mesh is still this value. So let's make sure that I update that. or maybe I didn't change it. So I'll go to assign and right here, go 48 inches, apply. Say okay. Uh, Anytime the analysis takes minutes and the structure is so small or it takes many seconds, you know that you have some type of instability or it's calculating some large deflections. It's basically iterating, doing various iterations, and something's going on. You see, this is the case. It's also still happening. So we'll have to ensure that we're modifying this thing correctly, even though we believe we did. Sometimes you have to go back and forth just to make sure. I don't know why, but it's sometimes it just doesn't take. All right, so it still did that. All right, to fix the problem, definitely, what we'll do is just say, we'll select this object right here, and then we'll say apply. We'll make sure that we have 4 feet. Say okay to this thing. Come back to shell. Edge overwrites. Auto cooking. We'll change this to 60 inches for kicks. Say apply. Now it should take. I should be able to right click in here and see that, but I don't. It just says floor meshing options. But I'll know when I run the analysis whether or not it took. Okay, so it took. It's going a lot faster. There you have it. I'll just go ahead and undo that. I really wanted that 4 feet, but this is not a problem at all. Um, let's just go back and 4 foot. It's not a big deal one way or the other, but for consistency, I want to use 4 feet. You have to make sure sometimes you go back and you change it to one number and then change it back to the number you really want that was working previously, and you get that going. All right. Now we can look at our live load deflection to make sure that it's rational as well, and we can do that by going to the display menu and deform shape, or using the icon, this icon right here. Load case, live load. We'll just be viewing it. I could show a shadow or not show a shadow. I could draw contours or not. Okay. Uh, Apply it. There's the deflection. It's rational. We're looking at about ½ an inch in live load. Okay. Start the animation, see what's going on. All right, looks pretty rational. All right, stop it. Now let's go ahead and check our reactions here. RAM, ETABS and RAM have different report settings. ETABS does a lot of tables, but it also has a report like a section over here. But just to do quick investigations, you go to their tables. So display, show tables. You can expand these boxes. You have information for the model, for the analysis, and for the design. So expand these boxes here and expand this result here and expand the reactions here, and at base reactions you'll be able to figure out what are the reactions. And so for dead load we have 293.076, which is exactly what we had in ETABS for our dead load, and for our live load we have 212.52. All right, so that's the exact same number. And if you don't believe me, I'll just pull up ETABS right now just so that we can refresh our memory. Close. Okay. Because I modeled the exact same thing in terms of member properties, I should get the same results. They're essentially using the same methodology, and this is available. They're competitors, so this is available for the use of the engineer in the same design office or anywhere. So I should be able to have the same results. So going to RAM frame, and from RAM frame, like I said, from our gravity loads area, we can come up with this. So this has 294.31 and 212.52. So cancel for our dead load. Let's see here. Let's just again 294.31. We'll investigate. Oh, yeah, this might be a little bit different, but let's take a quick look. And the difference is, let's see if it actually is different. It's a 1 kip difference. We'll figure that out later. But the live load is the same. That's interesting. But the live load is the same. We can make the calculation, see what it needs to be. Let me just take a quick look at my notes and see what it should be. All right, we'll investigate it later. But our loading should be exactly the same. So I'll save it here. All right, with that, we'll just pause at this point in time. Those are the basics of it. Next videos, we'll get into defining our wind loads and our earthquake loads, and our P delta analysis. All right. Okay, so we're trying to figure out what's going on with our self-weight calculation for our dead load, and let's run we ran the analysis and we came up with a value that was less than what we had in RAM, and trying to figure out why. So we have 293 here, and in RAM we have like 294, right? And the reason why is because when we defined our members, by default, these elements, these beam elements, they were canceled. Uh, they were modeled with the end length offsets automatically from the connectivity. So that means that the beams are modeled as actual length beams are shorter than they are in some instances. We can actually see that. So here, this is that setting that would affect it. This is dialog box that was affected, and the frame self weight option calculation is on auto. So that essentially is what happened. But just so we can see this thing graphically, let's go ahead and um, extrude our frames, turn off our top fills for now, say apply, extrude, say apply, oh, fill, yeah, it's weird, oh, that's odd, it should extrude the frame, auto edge, model's not locked, that's odd, the frame should be extruding here so that we can see that. Of course, there is some other button that's related to this thing or something like that. So let's see here. What would be the issue? Not quite sure. Let's say apply. Right, we'll go back and extrude it later. Maybe we need to turn off. I don't know. Again, program just acts up sometimes. Let's go ahead and make the modification. You see we were at 293, and we'll modify that to the actual lengths using the assign frame and offset command. Define lengths to keep them at 0, 0. You can modify this if you wanted to as a rigid zone factor. This is similar to the uh, web column, I believe it was called beam web or something of that name, rigid zone factor that we had from our RAM frame dialog box early on. But long story short, is this was the issue as far as the lengths. This will also increase your deflections. Uh, Again, our frame self weight will be based on this full length is automatically taken from our setting over here. So we could just always set it at full length, which is probably a good idea. We'll say auto, see what this thing calculates. Run the analysis again, and in a couple seconds, we can take a look at the table, take a look at the dead load reaction, and there we have it, 294.208, which I believe is pretty much, I mean, it's exactly what we expect in this way, just in RAM. All right, 294. Okay, so now let's go ahead and turn on our fill here. Let's see if this thing will extrude it now. So now it extrudes it. Take a look at what you have. And you can see that you're going directly into the joint beam column or beam to beam joints, framing to the center line. Whereas before, if you were able to extrude it and you can test it out, you'll be going to the face of the column. Therein lied the issue. All right, let's go back to our stick frame. Let's go ahead and define some load cases here, some load patterns and load cases with it. Let's define our wind load. Do wind. We'll do just the X and the Y individually. So wind X. You can do one and it can create all 12 cases, or you can take a look at it on an individual basis. So here we'll just do X and Y, which is great because you could just focus in on what are the worst case scenarios, and that is the case for us. Auto load can be taken from ASCE7. Once you add it, you can modify it. You have to modify it in order to update your, well, in order to fill out the right design parameters. Exposure and pressure coefficient. So it's asking you where you're getting the load from. Here, you had an open structure. You would use this from the frames. Here, we could do it from the extent of the diaphragm or the frames, the shell objects. So here, it's going to be our open structure. Now notice once I click on this button, all this area right here is grayed out. That's because you have to manually input your windward and your leeward um, coefficients onto the shell objects. All right. If I didn't do that and I did it from the extent of the diaphragms, I just had diaphragms, I could create all 12 sets, or just create, you know, one, case two, etc., etc. Uh, this demonstration will show how to do it for windward and leeward for your shell objects directly, because it allows, I believe, the greater variability. All right, so let's change to exposure C. Wind category, wind speed 115, gust factor, we'll keep it as rigid. Directionality factor 0.85 as well. Exposure from the bottom story, base, and top story here. Obviously, if we had a basement, it could be different. We say okay. keep it at that. Let's do one for the Y. Add that load in there. Modify it again. Same thing here. Say OK. We'll define these individually, like I said, on the shell objects. Let's also create our earthquake cases while we're at it. Earthquake in the X. Go ahead, seismic automatically. Yeah, cancel. Sorry. Earthquake X. Add the load. Modify it. Here we'll put in just the X direction for our directionality. Period would be program calculated. These factors apply for our model, 1 moment frame. Story range, same thing from base to the first story. These seismic factors are all 3. And again, our S of S value is 0.134. Our S of 1 value is 0.055. It will automatically calculate your SDS value for site class D. This is what we have. So you notice this number is 0.143 for SDS. That's the same thing we had in RAM, and same thing you should have on your paper already from your code analysis. You say, okay. You can also do this by zip code or longitude. Say, okay. Same thing for Y. Add the load, modify it, uncheck all these items, just keep Y. You could have a different system for whatever reason in the Y direction and the X direction. That's where you would put that information. So, okay. And with that, we've recreated those load cases. Let's go ahead and do the notional load case because we're using the direct analysis method. And we need to include it with all gravity, irrespective of if it controls or not. Auto, add the load, can modify it. This one is dead. Oh, we can call it notional. Now we have to call it notional dead because it's the dead load case in the X. So we'll do 4 X, Y, and live load and dead load. So okay. Let's modify the name of this. Call it NL X dead load. Modify. Let's go NL Y. Add new load. Modify it. Make sure it's the Y direction. Okay. Over here. Live load. Add it. Modify it. Make sure we use live load. Say okay. It's the X direction. Go ahead and change this to Y. Add the new load. Modify it. Change it to the Y direction and live load. Say okay. Now we have all of the lateral loads that we need to include in our direct analysis. So okay. Save the file. The wind load will be applied to plan elements. To boundary elements as shown in plan. So all I have to do is be in plan, and then I can come here and I can say define and say from the define menu, I believe oh, I'm sorry, I'm going to define to draw menu. Real quick, where are you, Mr. Define reference planes. Oh, I'm sorry. Draw auto cladding. So from the draw menu, you would draw the auto cladding. Use the floor for cladding options. This represents your envelope. Take a look at this thing in 3D. You see these elements were created, as well as pins were created at the bottom of it, at the base. And that's your cladding elements. These elements are shell elements, but they're shell elements without any properties, so you won't see any section properties. They're essentially dummy shell elements that are used for loading. So um, one thing you need to do is when you assign your windward and leeward pressure, you should know the local axis direction of the element. So here we'll go into here, this view options and turn on our shell elements, local axis, okay, apply. The way ETABS work is red, green, and blue is axes 1, 2, and 3, or X, Y, and Z, local axes. So just think of red, white, and blue, but instead of white, replace white with green is red, green, and blue for X, Y, and Z, or 1, 2, 3 axes. So we want to put it in perpendicular to, we want to put the pressure, windward pressure in the X direction, perpendicular to the windward wall. So it's pressing against it. And so here my Z-axis, if it's going this way, the Z-axis is parallel to our X-axis here, our local Z-axis. So we want it to go in the same direction. So I'll use a positive value here for my windward pressure. So I will select the shell elements, and then I go to assign shell. I believe this is the menu that you would use, shell loads rather, windward pressure coefficient. So for WX, windward is going to vary the windward pressure along that face. 0.8 is the coefficient that is used for our structure. All right, apply it. Come over here and do the same thing for the leeward side, but I have to put it in the opposite direction in order so that it can go parallel to the global x-axis, because my local z-axis is actually opposite to my x. All right. So long story short, read into it. We want the force to go the opposite direction. Once you define it, though, you'll see an arrow that pops up. I'm gonna clean this up a little bit so we can see our object better. Let me see this information to apply. Uh, take off my horizon just as well. Me and the horizon's constantly battling. All right, so you'll see this 0.8W and the arrow pointing that way. It's positive, so it's going in the same direction of the arrow. Here, when I select this element, define, obviously, I'm sorry, draw, again, wrong mistake, assign, shell, and then auto uniform, nope, I go to wind pressure coefficient. I'm looking at leeward, still using my X, and I have to say 0.5 here. Again, replace or delete are available, so keep that in mind, or add in the future. So apply. You see the leeward pressure is shown here, but it's a minus sign, so I know it's going the opposite direction in reality. Save. Let's do the same thing for the Y direction. In the wind load case in the Y, I select the element. I know one shell element is selected here, 4 edges. Come in here, shell loads, wind pressure coefficient, switch up the load case. I want this to be windward 0.8 to ensure that I'm going in the right direction. Take a quick look, say apply. Yep. Same thing here. Sign, shell, leeward this time, negative 0.5 in this case. Just make sure, apply. It's okay. I take care of the wind load definition on my structure. Earthquake loads are automatically calculated, but I will create a diaphragm just so I can track diaphragm properties, so to speak, or where that is located. Actually, this diaphragm is already created, so it's already defined as a diaphragm. If I want to create another diaphragm, I would do that here, or I could show what I have here for this diaphragm, rigid, semi-rigid. Let's make this a semi-rigid diaphragm and say OK. Select this element, and with it selected, I'll go ahead and assign that diaphragm to the shell. Apply. The graphics change up, and I have great. Let's see here, and I have an image showing me where the center of the diaphragm is located graphically. Change the plan view so you can see that clear. As we would expect, it's dead square in the middle. So this is actually the centroid of the diaphragm. Okay, so-called X sub cm and Y sub cm located right here. All right, we can find out information on this diaphragm as well. Let's exit out of here, reset the model, right click, geometry information, assignments that are here. It shows me I have a diaphragm. Any loads that are applied to the shell elements is provided here just as well. All right, go back into my 3D model. Let's go ahead and turn off our local axis to clean this up. Take off the horizon, apply. Okay. We can turn on our fills. It's not, let's go ahead and turn off the floors and the walls. We're done with what we need to do right here. So, okay. Save the file. All right. So now we need to make sure that we're including P delta into our analysis before we run our analysis. Actually, let's just go ahead and do a check, quick model check. See, make sure that everything came in nice and we didn't do anything crazy that affected the results somehow. All right, so we're good for what has been done. The model has been checked and no warnings were generated using that module. All right, let's do the P delta options here. This is basically the settings that are available for creating P delta effects into your structure. You can have it on the none, which means that you would be using the nonlinear load cases and explicitly defining P delta in the load cases and load combinations rather. You can run it on combinations. Remember, this is ASD design, so we actually have to make sure that we're at the ultimate load levels, and we need to use factors that would correspond to that. Okay. The difference if you're using an iterative design or so-called rigorous second order elastic analysis versus an approximate one. And this is somewhat of an approximate one just as well. But It actually does an iteration here um, as an option. The other option is non-iterative, which means that it could be based on the dead load. The dead load remains stagnant. This is normally done when no loads are defined in the model, and you just have your frame and you wanted to analyze the self-weight, and you had static load cases here. But if you have loads, this is what you need to use. The load patterns and scale factors should correspond to the critical P delta load case. You can read into this from ETABS. There's a nice write-up on it. These are basically our same ultimate load factors that we used before uh, when we did RAM. So we'll bring in our dead load and our live loads as our preset P delta option. This basically includes, make sure that P delta effects are included in the analysis of each linear case, and then the results can be superimposed together because you're just doing a first order linear elastic analysis. Let's say okay to that, and we're good. We'll show the effects of using that P delta option and uh, the more rigorous approach as well at another point in time. But right now, just to get some consistent results, we'll do the same thing we did in RAM. RAM does not allow you to do the rigorous analysis, by the way. ETABS does, which is great. So with that, we have these load cases that were defined. So as we were doing our work, we were actually creating load cases just as well. So just so you know, we have each one of these individual load cases defined. And we go to our, analysis menu, and we can take a look at the load cases and what runs and what doesn't run. Again, all these are linear static, but they have a pre-delta preset into them right now. Say okay. Then we could actually create load combinations based on the code, and we could bring in all our still default combinations. I would like to make them user editable just in case I want to modify something in the future. So I say okay to that. And we have 40 load cases that were created. They're less than what is in RAM because I didn't create those 12 win load cases. Instead, I created 2. So we have less permutations for win load case. You can go into it and see what it is, each one of these combinations. You can hover over it and you get a quick preview of what it is too. Dead load with the notional load and the X direction, and you can see the first portions of these all essentially gravity loads with notional loads combined with them. Then you finally would get into your lateral load. Looks like about 16 to 17. You kind of get into your lateral load, 17, 18 for wind load cases, and the permutations for the different combinations. Then later on, of course, earthquake, same thing. And you can notice that it's already been factored. The dead load has been factored to include the vertical earthquake effect just as well. Let's say okay, save. Now let's go ahead and give it a shot. Run the analysis. Okay, quite a bit of dead load deflection here. Let's investigate that for a quick second, see what's going on. Let's put on our, no, we don't have an issue. I mean, it's not crazy. It's probably some local stuff with the shell, with the membrane itself. It's not the beams that are kicking up like that. That's for sure. Let's see here. Put in the fill. Show our floors. Say apply. Yeah. So yeah, some local results, giving us some interesting analysis. Start the animation on that. Nothing to be concerned with. We could modify that later, but it's not going to affect our frame analysis or our beams or columns or anything like that. But if this number was crazy, like 4 billion or millions or hundreds of or anything like that, we'll want to modify that. All right, so I will go ahead, and so now we want to go ahead and do the steel design. Let's make sure that all of our frame members are included in the design. I will show the underform shape and go ahead and turn off my walls and floors so I can have a better look at what's going on with the columns. Turn on my member sizes. Just hit the design button. Oh, okay. So I have a dialog box that pops up, and it's just basically telling me that um, some of the stiffness values has been modified. That's for 20 members. Um, those are, to be honest with you, probably related to our simply supported ones, which is an interesting thing for ETABS because ETABS includes your gravity beams into the lateral frame analysis and reduces the stiffness. That's not necessary, but this is what occurs when you're into just one module. It'd be nice to be able to say these are all gravity and don't include them into the lateral frame analysis for direct analysis, therefore don't reduce the stiffness. But this happens. So it's asking me to reiterate the design, the analysis and the design, and we'll do so. You can read into ETABS manual to find out more information on this dialog box. We'll say okay. It reruns the analysis at least once and goes through the design check again. So there you have it. These are the members that were designed automatically. Um, the ones that are in blue are the ones that actually were designed to have values. The ones that are in white were not included and were not designed for whatever reason, probably for the stiffness properties in this case. All the columns were, but just to take a look at what's going on here, I can display the design information by clicking on that I-beam icon or going into design, still frame design menu, if it stays still, and say display still frame design results, apply, and I can see what are stress ratios that are shown here. All right. Now, if I want to make sure I include everything into my analysis or my design, I want results for everything, all the frame members, I highlight them, and then I go to my design menu, overwrite frame design procedure, still frame design, make sure that they're included, I do believe, and run the design option again. Let's see if that works. If not, we'll take another step. All right, seems to have done the trick. And since nothing is in red, that means everything is working. And these are the results. So again, I can take a look at the ratios here, investigate in greater detail, cancel, and apply. I can see that I have 0.125 for my columns here, and the control and load case, if I right click on it, it will give me, it's the load combination 29, and I can find out the details of what's going on here with this column. Take a look at my results. This can be printed. It's a nice printout to find out information. Um, there are some limitations to this, but it's very useful. It's very good as a summary, but as usual, structural engineering, you have to go and investigate details for yourself. Like this load case right here, 29. Let's see which one that is. We will go into our define menu and load combination, load case 29. It's this one. Modify show combination, just the earthquake. So okay, earthquake in the X direction. It's controlling. You can see that these values actually they work just like they worked in RAM, and they're comparable. So the last thing I'll do right now is just show what the report is for this project, and it gives you a great summary. ETABS does a good job in this just as well as far as generating an automatic report. Once you double click on it, it will generate the report. And then they give you a tab to view it. A nice little model up front. You could zoom through here and you could take a look at something like earthquake, for example. It's all kind of information, beam connectivity, story data, diaphragm masses, like I said, your diaphragm central points, XM and CM. See it right here. Very good information. Some of it is not related, but it's it's necessary. Auto wind calculations for your wind. You can see 15.5 or 15.6 kips were created for the X direction. Let's go to RAM and see what RAM said. And under its load and applied forces for the wind in the X, did it come up with 15.6 or are we crazy? It should be something similar. All right, 15.5. There you go. Wind X. That worked. Let's see what RAM has for the Y. 19. Okay, great. Let's see what ETABS has for the Y. That's the Y case, 18.6, 19 for all intents and purposes. Keep it moving. Let's go to seismic load calculation. It gives you nice detail. Oh, come on. Good. Seismic load calculation here. That's the forces. You can see that it used 283.4 as we would expect it to, because it's only using half of the column tributary to the bottom. It's the same thing as ETABS. It's 283.4. I mean, same thing as RAM. Get into RAM. Take a look at what RAM has for its effective seismic weight. 283.4. Dead on. Came up with our CS factor that's used as 0.048 or 0.48% of gravity. That gives us multiply that by effective seismic weight, gives us 13.51. 13.51. All right, same CS factor. So we have converged with our lateral load analysis for these two models and our gravity load analysis, and we could look at it in greater detail, but I could tell you it works. With that, we end, and we've completed our direct analysis for this model. We could check things like deflection and sway and things of that nature and make sure that we're all good and go into the stability coefficients. ETABS doesn't do the same type of validation that RAM does for our RAM. So, for our analysis, direct analysis method, you have to do that yourself as an engineer using ETABS, and it's expected, and it's not a bad idea. Like I said, RAM, you can't use it as a crutch. Even though it's giving you that information, you still need to ensure that it's right. So P delta was included also, just really at the joints. We could break that into two If we want to include P small delta effects, we have to break the column into two. It does it automatically using internal meshing. So it captures P capital delta and P small delta a little bit, but if you want to capture it in greater detail, P small delta would be captured by breaking these frame members into two elements manually. And I'll show you how to do that. You'll see that my values won't change here though for this model because it's not that sensitive to P delta here. So check this and let's just do that real quick. Select all of our, and we could select all of our 14 by 90s by just selecting filtering our selections, selecting the properties of 14 by 90s frame sections. I come in and say, hey, grab all of 14 by 90s. If all my columns were the same, it grabs them. I should know that 16 is selected because it's right here, 16 selected. Take it, let's divide those elements into two, break them into two. It gives me a preview of what's going on by those flashing blue dots. Say, okay, apply it, run the analysis. Takes a second longer because there were more elements created. Let's go ahead and, oh, now I'm even getting even greater deflections. Well, interesting. This is not good. We have to go investigate why. It's probably related to our shell elements here. We'll have to go back and fix that, but it doesn't affect our analysis, our still results here. Those are related to the shell elements. And rerun it. Let's go ahead and take a look at these ratios. You can see I still have 0.125 is the greater of the two ratios here on this column, and that's because the controlling location is actually at the joint of the beam. All right, and the column. So with that, we'll put it to an end. Again, like I said, our deflection issue is related to our shells and the meshing not affecting here. Sometimes you don't even need to model that mesh if it creates too much of a problem. You can put some of these forces directly, um, and that helps. But it's just it's important to model it sometimes. It gives additional stiffness to the structure, so it's not a bad thing, but it can be troublesome, and you have to kind of treat it with kid gloves. Make sure as an engineer you pay close attention to that area. Go into it, take a look at it real quick. Turn on the floors, apply it, see what's going on with the mesh. Take a look at the deflection, dead load case, apply. You can see what's going on. It's along the edges. Some funny business that happened after we created the envelope. All right, so once we created the cladding, things kind of went haywire because there's some meshing that happens with the cladding elements just as well. All right, but we're good. So it doesn't affect the lateral frame analysis, and as an engineer, you have to understand that. Let's save the analysis, and that's it. Video completes. This is a completed video for comparing ETABS and RAM just as the stage. We will go on in the future and do some more comparison, but just these are the basic procedures that are required to model a building in 3D, a steel building in 3D. Same thing would apply for concrete buildings just as well. We'll do videos on that in the future. All right, that's it. Okay, picking up from where we left off, uh, we had completed the analysis, gravity and vertical, gravity and lateral, and we realized that even though the analysis ran and the members, the member sizes were analyzed, we can determine the capacity ratios, we still had deflection issues at the edges of the deck itself. And so I investigated what was the cause of that issue, and it turns out to be related to the stiffness properties of the metal deck when using a semi-rigid diaphragm. If you could recall, there is a step where we have to define what our diaphragm is. I don't know if you have to, but this is where it's recommended definitely to do so. And so when we define that diaphragm, we have the opportunity to call it semi-rigid or rigid. Those are the two choices in ETABS. And so the previous setting had it as semi-rigid. And when you combine that with the meshing that takes place with our unfilled metal deck, you can see that the properties of this unfilled metal deck is really something that results in flexible mechanical properties. And so we were getting very large deflections on the ends. And I suppose it's fairly rational as far as having that type of deflection. But our design shear thickness here is only 0.0358, which is related to a 20 gauge metal deck. So the self weight, just on the self weight alone, it was deflecting, and definitely self weight plus the additional superimposed dead loads and live loads, then we had even greater deflections. So the way that I fixed that issue was to realize, of course, that this metal deck along the edges, as it protrudes away from the center line of the beam, we have a deck that cantilevers out 12 inches, for example, from the center line of the beam. We would normally have a plate in that situation along the, if you will, the weak axis of the deck span. And sometimes we just have this plate around the entire perimeter. We have a steel angle, like a deck edge angle. And that angle could be something like 1/4 of an inch or 3/8 of an inch, some type of bent angle. So it's not uncommon to have something like that in the normal situation. So what I decided to do was to actually model in that angle, if you will, or a plate with the stiffness of a 1/4 inch of steel, and place it along those along the perimeter. And so you can see what I'm talking about here. You can see that I have different area elements here. This is our main deck that is outlined. All right, this is the main unfilled bare metal deck, non-composite, nothing like that. So it's just our deck, and the framing of it is along the center line points of the beam, and it's connecting at the nodes, at the columns, etc., etc. All right, now outside of that, so we zoom into here, you can see I have these nodal points, joint 67, 70, 16. Right, so right here is where I have, excuse me, is where I have our metal plate modeled in. You can see these are two metal plates there, more so ends, and let's see another one over here. Okay, so that's the fix. That's one thing to fix it. Another thing would be, uh, you know, when you're doing these structural analysis, you don't have to try to be as what you as realistic in every single aspect as you might um, have in your construction documents. You know what in fact is that we're after is the structural behavior. So even eliminating this extension right here, it's not will not cause a significant error at all. Especially when the cantilever is small and the additional weight, you know, um, from it's really from self weight is not going to affect you, and any additional weight that occurs from snow or something like that, just rooftop, it's a small amount. So you're not going to be affected that much. And most certainly, if this was a floor, that additional weight wouldn't make it an issue at all because it's actually highly unlikely that you're going to have that type of uniform load along the edges as well as the interior. All people gather in the interior space. That's where the load is. Everything else is really fictitious as far as spreading that uniform load over the entire area. What is the worst case scenario as far as loading is concerned, gravity loading is concerned? Get your maximum loads. So that's why it's done. All right, so let's look at one of these properties. You'll see that this is I defined a section property called the steel plate, assigned it to that element. It's a shell element, and you can find out more information about it. Going to section, define, side section, steel plate, show the information. It's a thin shell. At this moment, finite element type, 36 KSI, gave it a quarter-inch thickness, and the property type of slab. So that's what I've done. Take a look at the results of what I've done. We're going to undo it, show the other scenario, and then redo it again just to be even clearer about the effects of the modeling. All right. So here I will show the analysis has already been completed. So I will show what's going on with my vertical load, deflection under gravity. Take a look at this thing in 3D, and you can see that this deflection that's occurring is very small. Look at our numbers now. Now we're back to the half-inch minimum as far as negative deflection is concerned. And really, that's occurring actually inside here in this area right here. If I turn off my horizon and contours, it'll probably be a lot clearer. So I will go ahead and do that. You can see the deformation that's going on there. Okay, I do it in 3D. You can see the greater deflection that's happening at that first bay, as would be expected in a metal deck and a small. All right. Load wise, though, everything else is pretty much remain the same as far as load distribution is concerned. All right. Okay, so that's an example of the results of how to fix the problem. Go ahead and take a look at the problem itself again. All right, and I'll do that by just reassigning these edges that I've created to the same thing they were before. Okay, so as area elements, I can just change the property, apply it, say okay. Show you some interesting things that happen here that could lead to I guess, unrealistic results. Let's turn off my local axis just as well. Force back on. And you can see each one of the area section has the deck property on it. Don't worry about the span right now. And at this point, as far as the span direction for these slivers, for the most part, we're doing the right thing. Everything, it's fine. Okay, so with that in mind, and keep in mind that this has the property of a semi-rigid deck. Let's take a look at it. It's a diaphragm D1, semi-rigid diaphragm. To this is typically defined as semi-rigid. Put this thing in 3D. With that being the only modification at this point, go ahead and run an analysis. Okay, so you see that the results have dramatically changed for our dead load. We have 1.2 inches as our deflection here, and that deflection is happening as we would expect along the edges. All right, this area. Okay, so that's a demonstration of what the problem is. Now, let's go back and see the effects of what happened, what would happen rather, if this was still the exact same properties that we have for our bare metal deck, our unfilled deck, but the diaphragm was so-called defined as rigid, which actually may not be applicable in these cases. It's definitely not normally applicable. But rigid diaphragms, are very stiff, and all the nodes in the plane tend to move uniformly. The load distribution is different. All the fun things that happen when you have rigid diaphragms uh, would be represented in this analysis. Okay, so I'm going to go ahead and change my diaphragm property to rigid. And when you do that in ETABS, you actually still need to go back and reassign, if you will, that diaphragm to those same elements. If you do not do that, notice that it doesn't take just because I changed the definition of it. In one area, I actually have to reassign it. All right, so that's been done. Now with that modification, run the analysis again. Recall last time the deflection was 1.2 inches with a semi-rigid diaphragm. Here, in this instance, look, we have a ridiculously large number. Looks like it's about 213,000. Right, so with that, in terms of deflection, we don't even know what's going on, but I mean, this is related to the mesh or something. Okay, so it didn't mesh with the adjacent element. That's not always the case, so let's just make sure that the two would mesh. It's more representative of what I had in mind here. So that's just an example of what happens when you have rigid diaphragms. So you're meshing the diaphragm, and you have different shell elements. So let's ensure that all of our shell elements will have the same floor mesh requirement. Okay, mesh it. Auto cookie cut 48 inches. Let's ensure that we also do something called, let's see, edge constraints, auto edge constraints. We read about this. Typically aligns your, well, it makes the model moves together better. You have these weird settings. This is all things that are fun and germane to, excuse me, germane to tabs. Let's select it again. Let's make sure that when we go to our analysis, this might not apply. We still have that setting from our analysis on the flourishes as well. All right, so it should be different. Let's run the analyses. See what happens. Now, sometimes the program takes it, sometimes it don't. It does what you expect, sometimes it doesn't. So here, depending on the mesh, oh, this is what happened. I mean, the deflection became even greater. Some local things. This is a local meshing issue with the way that I've actually modeled these shell elements. All right, that's why you have this like crazy deflection out here with the rigid diaphragm effect. All right, so that's what happens when you have these slivers and those rigid edges. Now, we're going to do a thorough review here. We know what happens when we have our slivers, right? What happens if I delete my slivers? They have the same properties. What I wanted to do was to have the deck extend out 12 inches itself. And so it has the same properties. At least those areas had the same properties as the deck, but we're having some meshing concerns. This one is more uniform, monolithic in this method right here. So I'll just take it and like we did earlier, and we will expand the edges of this thing 12 inches, they apply. So, still one area element and not 5. All right. Nothing has changed other than my expansion of it. All right. I don't have any slivers anymore. So it's more monolithic, if you will, from the finite element perspective. And recall, we had very large deflections before using the rigid diaphragm and the slivers. Let's see what we get this time. Okay. So this is the results that I was expecting. And you can see now we have very small deflection. Again, with the rigid diaphragm property that's set here, which is actually incorrect for metal decks, or typically would be incorrect. You would have to go through a certain analysis to determine if your diaphragm is rigid, but most likely than not, the diaphragm for metal decks is kind of almost always treated as not rigid, unless ASE tells you to treat it as a rigid diaphragm by some type of an analysis. But either which way, that this diaphragm, would be a semi-rigid diaphragm, right? It's the only other option. So it's in the code to do that, and our computer software have the technology, have the power to do that. So that's why it's actually in the code. They expect you to use a computer and check this thing out. All right. Okay, so as an engineer, you can get this result and you can think, oh, everything is fine. I have small deflections. It's behaving like I expected. All right. Everything seems fine there. You go along and merrily. Just Go ahead and run your analysis. Run your design. Come up with everything works, no problems whatsoever. And you're saying to yourself, "Oh, this is awesome." Okay, but you're not um, right. It's incorrect. The settings of the diaphragm is incorrect. You have to modify that. So let's go back to our modification of what we had in the beginning. Semi-rigid diaphragm. So let's say I realized, oh man, I made a big mistake going back and change this thing to semi-rigid and go through the procedure that I need to change it semi-rigid. Run the analysis. It should take me back to my, kind of like large deflection on the edges issue with our metal deck, and that's what we have here. That's why you get this almost 2.6 inches on the edges. Okay, so you don't like that either. And deformation, because this thing is scaled, you're not seeing the results that you would normally see at this particular scale. You have to modify and see else what's going on, but if you change the scale and increase it, then that changes the scale on the deck. You have to turn the deck off and take a look at some other things. So it's a hassle, right? All this because of meshing semi-rigid diaphragm with essentially small structural stiffness properties, right? Relatively speaking, small for decks. All right. So, as I said, the way we solve this problem is to take this deck, bring it back inward 12 inches, apply it. But you would investigate and see what's going on. So let's say that's the only thing that I did there. I have joints that's not attached to any element or anything like that at this point. So I'll check my model. We'll see what happens. Select all. Sometimes the computer picks up on this as being an issue. Some software programs will say I have joints, but I don't have any properties or anything assigned to it, and it's just like a random joint floating out in space, so it'll pick up on it. Some softwares don't really care. So that's the case here. And that would have been joint 7. I would expect it to pick up on that. Other softwares would pick up on those joints. At least at the corner, I know I still have my shell elements. So that's probably why I wouldn't get a error message at that point. But the other joint that's not framing into what was expected to be an intersection of elements, then I would expect to get some type of error. But it's actually not a problem for ETABS, so that's a good thing. Let's go ahead and run the analysis. Like I said, the only thing we did was bring this thing back in and tied it to the framing itself, to the center line of the framing, which is not a bad idea. In fact, if I had really big problems with my model, that's exactly what I would do. I'll put any additional loading that happens at the edges in my model directly. So I'll figure out a way to create the structural model that I need to analyze. All right, so when I brought it back in, again, we're back to the 1/2 inch. That's rational. That's what happens on the inside. But I, still don't have the edges in there. And for whatever reason, let's assume that I wanted to have the edges in there. So then I would come in here, and like I said, I put in a steel plate. Okay, I got rid of my little window. Turn it back on, but it's not necessary. Let's go ahead and use steel plate. Grab it from this joint. measured out those points to be 12 inches away from this center line of the edge beam. Put this one up here. Take this one. Right. Grab a point. We should grab a point on the edge. All right. This is the fun part. So let's just make sure that we have our snaps set in the sections. Get back into the command, make sure we're in it. There we go. All right, there we go. Select everything once again and make sure we are applying some type of mesh to it. We don't have to always. 4 feet is a decent number to use to apply. I'm going to ensure that I do my auto edge constraint just because I like to do that as an additional box to check, so to speak. When I do that auto edge, I get this dialog box and it basically says it's going to create these edge constraints. And I also have the option of not only doing it for walls and floors, but for everything in the structure, not just what's selected. So apply that. Select these things again, go to diaphragm, and semi-rigid, it's fine. But I want to ensure that my new elements are included in the diaphragm calculation just as well. So I go back and I assign it. Sorry, picked the wrong command. Apply. I could tell they're included because my white lines, dash white lines, extend to their edges, their points. So that's cool. Put this thing in 3D, Dumond deform shade. Let's go ahead and turn off my nemesis, the horizon, right now. Run the analysis. We should be back to the point that we started at when we started this video, so you can see the reflections below. Once again, and everything appears to be working as we would expect it to be. All right. Maybe some edge issues, some crazy funny stuff that happens here and there. It might look like that. Go back and investigate, but it appears to be fine right now. Okay, so you know, we could turn on our contours just as well. You can see that there are variations of the deflection along that edges. So that to me is you know, obviously indicating that it's picked up on the beam elements and it's connected, and we are getting a stiffness distribution in vertical direction that we would expect. Okay, so you can see the variations, larger deflections out on the ends, almost nothing at the supports itself. Excuse me, these deflections are also very small. with the exception of the 1/2 inch that's happening in here. And that's probably fairly halfway realistic for this situation, but not realistic in construction. So if you were actually putting your deck there and you're spanning it this direction, and the self weight alone, you will not get 1/2 inch deflection. All right, but in the finite element world, for what we had to model, that's what we have, because that's the moment of inertia was calculated, the stiffness was calculated based on a 20 gauge plate, really. All right, so with that said, we'll go ahead and run our steel design. We had already shown that everything was working fine. Okay, let's go and investigate some smaller things here. This design, I had to go through a process of figuring out what the problem is. So it could be like that I don't even have the wind loads included in this anymore. And so you can just go back to the analysis from before. Well, I'll do another video where I include these loads so that you can see that all loads are included here, even though the load pattern might still be here. The actual load on the cladding is probably not. Let me just go ahead and investigate that. The reason why I know something's, it's obviously different in the colors. Everything is in light blue range right now, whereas before we had the variations in our colors, and I would expect that for the gravity beams. All right. No, sorry. So I have my elements on, right click on them. Deform shape, right click on them. All right, let's see if the loads are there. So you can see I don't have any loads on my walls. I had the walls there. All right, so it's not a problem to do that. It's fairly easy. And I will go ahead and turn on my local axis and reapply some wind loads here. So remember, we select the area. We would show also the direction of the local axis because we're going to assign to unlock the model. It won't let you make any modifications without unlocking the model. So come in here, shell loads, wind pressure coefficient, 0.8, going in that same positive. It's going to replace whatever might have been there. There's nothing there. As discussed, you see our arrow with our positive 0.8 in the W there. Select the other end. Do the same thing for the leeward side. You can also put side pressures in, which is also cool. People forget about the side pressures oftentimes because they think about the total windward and leeward, but that side pressures could have an effect on your building too. As it's bowing out, it actually adds stress. So you have to ensure that if you think it's applicable, you include it. All right, for our little video here, we're not going to do that. Apply. There you have it in X. Let's do for positive Y. It's kind of long to do this, so we'll have, this is not the only way, but this is the long way, if you will, to applying this. Definitely not have to do this on an individual basis, but when your building is fairly irregular, you may have to do that, and that's why I'm showing it here, even though our building is not oddly shaped. Okay, so that's in now. Save it. Earthquake, you don't have that problem, so earthquake forces are still in there. As well as notional. Run the analysis. Okay. Similar results. Let's make sure that we have all of our little combinations defined down here. Oh, I remember. Also, probably don't have. Let me before I delete that. Oh. So it's going through the process again. I didn't add any additional superimposed dead loads or live loads or anything like that. You can always go to your model and check that out. So the slab is not loaded. That's the reason why everything is still in the cyan or baby blue color. Let's put some weight on this thing in addition to the loads, lateral loads that we just added. Then at that point we'll have the full kit and caboodle, as they say. This is a good demonstration to show you that you have to go back and investigate your model and your design. It's definitely an iterative process. And as an engineer, you need to be aware of, in my opinion, you need to be aware of when you're probably wrong, even more so than when you're right. That's the one thing that has guided me throughout my career. I'm not always 100% sure when I'm absolutely right, but I am oftentimes 100% sure when I'm absolutely wrong. And I know those results are absolutely wrong and not what I expected. So you have to go back and check and see, hey, did I model my gravity superimposed dead load? Oh, no? Well, let me go ahead and do that. Select the objects that you had previously selected by going to the selection menu and get previous right here. Or Control J. So with that, also I could use this icon to assign my frame loads, my shell loads. I'm going to go ahead and do the manual thing. Right. Okay, now, if we run the analysis and we don't have variations, then we know that something is really wrong. Okay. Then we would have to stop the video and do something else. All right. You can see that dead load increased. The dead load deflection increased. Let's go ahead and run this thing. Try to get some indication that, there you go. Things have changed a little bit. There you have it. That's a variation. Let's turn off our horizons. This doesn't mean that it's all done. It's all done. You know, I still will go back and check some things. I still will go back and verify that the proper design method is being used. That's because I went back and forth with this thing a few times, but I could take a look at my so-called load and moment ratios, axial forces and moment ratios. As far as our capacity is concerned, demand capacity ratios. Take a look at that. Yep, kind of what I expected, exactly what I expected. I wanted to investigate a beam. Take a look at this and see. This is gravity beam. So expect a gravity load case to be controlling. It's number 15 here. We have to go into it and figure out what it is. But let's look at the details to make sure that, okay, let's treat that an ordinary moment frame, which is fine. 100% fine. Choose the ASD. So everything looks to be fine here, except for the fact that this gravity and it still reduced the stiffness factors by 0.8, well, 2.8 times EI. Not applicable for gravity members per se, but it's okay over here. Let's just take a quick look at what deflection is. That's the wifey calling me, trying to figure out where I am. I'm supposed to be on my way to pick her up, but instead I'm making videos. She's in New York and I'm in DC or Alexandria. Anyway, long story is go back in here and check this thing out. Let's see if the load case makes sense. Yes, it does. Dead and live with the notional loads. We expect dead and live to control a gravity load beam here. Notional loads are added because that's what this thing does for that load case. All right, so this is what we expect, and everything appears to be fine. We don't have any particular issues. We can come in here and divide this thing up again. Let's take a look at the details. Yep, all the other settings that we previously had to the frame members are still applicable. Don't see anything funny going on here. Take a look at the controlling load case here, so-called 29. Ultimate strength design, still 29. Let's look at what load case 29 is about. Load combination rather 29 is about. And again, these are linear load combinations. They're not nonlinear. They were combined algebraically, if you will, using the principle of superposition from the analyses of individual load cases, dead, live, earthquake. But those load cases were also created using P delta effects that modified the linear elastic structural stiffness matrix so that we in the end included P delta effects in our overall global analysis. So it's a long way of just basically saying P delta effects were included, but this is not your typical iterative P delta analysis of load combinations. Instead, it's an approximate method that was used to include the P delta effects by modifying the linear analysis directly. All right, so modifying the stiffness matrix. Talked a lot about that. You can read even more. All right, so anyway, earthquake controls this thing according to this analysis, at least at this case. And I think that's good enough to say that we're okay with that. And wind probably can control it just as well, but we have to go into here and take a look at the value that we have for wind, and we ensure that it's probably something very similar. Let's just see, wind was included. I have a bunch of earthquakes. A bunch of earthquakes is wind. Which one is this thing? in the x direction. So let's just see what happens when we have wind in the x direction. Well, it says 0.13, just for kicks. But we'll take a look at what we have when we have wind in the x direction with dead and live. Right, this should be a good combination to review. At 17, come in here, see what we have on the 17 at the same location. 15. Virtually the same number. Okay, 0.13. All right, so with that, we'll conclude this video and our comparison of ETABS results with RAM results using, well, I guess, a modified P delta analysis that that allows us to combine the linear elastic load cases algebraically instead of having to run P delta analysis on load combinations directly, as is required when you use the iterative method and so-called rigorous second order elastic analysis. All right, well, that's it.